Hi, my name is Evan Beach. I'm a research scientist at the Center for Green Chemistry and Green Engineering at Yale University. I'll be your instructor for these modules. Applying the principles of green chemistry. In the first lesson, we explored the 12 principles of green chemistry and their history. In this lesson, we're going to focus on how they can be put to use in the real world. In this first module, the metrics of green chemistry, we're going to look at why we need to consider sustainability in the chemical enterprise, and how the 12 principles can help create a more sustainable brand of chemistry. The first question we have to ask is, why should we care to develop a more sustainable, greener approach to chemistry at all? Haven't we been doing traditional chemistry just fine for the last 100 years? Why change anything? As you'll see, we really don't have any choice, but still, not everybody sees it this way. Too often there's an attitude that it's just not my job. But think about what would happen in other professionals if our careers took that same attitude. So if you went to a restaurant and your chef said, "The meals I make are delicious. Sure, they're poisonous, but there are other chefs working on non-lethal cooking." Or an architect says, "The homes I built are luxurious and attractive. Yeah, they collapse and kill people on a regular basis, but there's other builders who are working on safe housing." Or your car designer says, "I build the most beautiful and fastest cars in the world. Yeah, sometimes they fall apart and explode unexpectedly, but there are other car designers working on sustainable cars." It sounds ridiculous, right? But is there really any difference between those examples and what a chemist might say? I developed some of the best methodologies and processes for making hundreds of target molecules. Sure, sometimes they harm humans and the environment, but there's other chemists working on green chemistry. And so what's the result of that kind of thinking? Well, go ahead and take a deep breath and try and hold it for 10 seconds. Okay, go ahead and breathe out. In those 10 seconds just now, when you took that deep breath, a series of damaging events unfolded around the world, and all of it happened because we're not practicing sustainable chemistry. So in just those 10 seconds, more than 36 tons of hazardous or toxic waste was added to the world. Almost 3,600 tons of fuel were consumed. Nearly 10,000 tons of CO2 was added to the atmosphere from the burning of fossil fuels. And almost 5 acres of rainforest was destroyed, just 10 seconds. So obviously we can't continue on this path. We have to start practicing a more sustainable form of chemistry. And let's go back to the definition of green chemistry. It's about the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. And it's only by designing from the start against trouble later that we can build a truly sustainable society. And so here's what happens when there's no design, if we just create a chemical or process without thinking ahead. So a chemist invents a new chemical or new chemical process. It goes to market, it gets used commercially. If it starts building up in the environment and doing damage, eventually everyone will agree that's unacceptable. And so then legislation is debated, and there's market pressure and consumer concerns that restrict the chemical's use. And in time, chemists will be called on to do new research and come up with a replacement. And if nothing changes, we just start all over again, repeat the cycle, and the result is a waste of time and money that could have been spent on research. And in the meantime, we've just added more toxic waste and done more environmental damage. But fortunately, we can break this cycle by using the 12 principles to guide the design of new chemicals so that they're truly sustainable. Well, how do we do that? Let's take a deeper look. Principle 1 essentially states it's better to prevent waste than treat it or clean it up. Or to put that another way, an ounce of prevention is worth a pound of cure. Sounds like common sense, right? And that's the promise of green chemistry. But to fulfill the promise of the 12 principles, we need to first address 3 crucial issues. And those are a chemical's life cycle, the hazards of a chemical and its processes, and what we'll call for now the human factor. So let's start with those first 2. Like every one of us, every chemical has a life, from birth to death. In the beginning, chemicals are built out of raw materials, like petroleum, coal, wood, agricultural crops, water, minerals. Chemists refer to all these things as feedstocks. And then the feedstocks have to undergo chemical processes and transformations, and sometimes these require different forms of energy. All of this creates waste and byproducts and co-products. Sometimes these things can be recycled, sometimes not. But either way, a product's life eventually comes to an end. And the point is, we can't judge the overall sustainability of the life cycle unless we're paying attention to it the entire way through, and we're drawing on the 12 principles at every step to ask some tough questions about the hazards. For example, are the natural resources we're using inexhaustible? Or are we designing chemicals that do not persist in the environment or are harmless to the environment we rely on? And are we at least minimizing hazards and toxins when we design a new chemical or a chemical process? By asking questions like this, we can use the 12 principles of green chemistry to identify what are the most dangerous elements in a chemical's life cycle. So let's look at plastics as an example. The feedstock for most plastics is oil. Is oil a renewable resource? No, not on a human timescale. And do we focus on minimizing hazards during the creation of plastics? No, at least not very well. And are plastics biodegradable? No, typically they persist in the environment. And this is just an example, but the inescapable conclusion is we need to rethink from the very beginning how we manufacture plastics. But that's easier said than done, and that brings us back to point number 3. When we talk about taking greener approaches to chemistry, we have to address the human factor. Because change will never happen if we don't meet the needs of the many kinds of people who have a stake in chemistry. And that's not easy. And why is that? First of all, because change of any kind is hard. But the chemical enterprise is also a huge industry with millions of workers. It generates trillions of dollars in income. So it's not an exaggeration to say that it touches almost every aspect of every person's life on the planet. Because of its immensity, it involves a wide variety of people with a wide variety of viewpoints. Chemists and chemical engineers, of course, but also factory workers and government agencies, business, consumers. And each of these players looks at chemistry from a different perspective. Government agencies like the US EPA or European Environment Agency, for example, they're there to protect citizens. Businesses are in chemical enterprise to generate income and produce profits for their investors and people who work for them. Factory workers rely on chemistry to make a living, but they also have to worry about the danger of their workplace. Chemists and researchers create the chemistry that makes everything possible, which is how they make their living. And then the rest of us use the products that the whole enterprise produces, but we too have to be aware of any damage that these products can cause us or the environment that we rely on to live every day. For these reasons, it's important that green chemistry tools and benchmarks are meaningful and useful to all these diverse groups. For example, the amount of waste generated in a chemical reaction could be expressed in a variety of ways. Chemists might speak in terms of atom economy, since atom economy is an enhanced measure of reaction yield, and that's something that chemists are used to dealing with as part of their training. E-factor, reaction mass efficiency, carbon efficiency, those are other benchmarks that might make more sense to engineers or safety officials. And if you're a business executive, probably the cost of the waste and its effect on companies' profits would have the most impact. So the point is that green has many shades. And it's challenging to balance the social, economic, and environmental benefits against the trade-offs that are needed to create a more sustainable society. But the principles of green chemistry are designed to minimize trade-offs, and they can help us to improve the sustainability of a chemical product or process. And if we don't make a conscious effort to use cohesive design guidelines that address the diverse needs of everyone with a stake in chemistry, there will be no chance of building a truly sustainable approach to chemistry, and no chance for real change. So, we can begin to meet this challenge by using the 12 principles in 3 important ways. First, we need to know what is and what is not green about a chemical process. And we use this information to develop more sustainable solutions to the problems we identified, and then put these in place to evolve the truly sustainable solutions. And we'll tackle these 3 challenges in the next 3 modules.